So hello and welcome to this session about the domain name system in the networking basics series. I am Apurva Todkar and I run the DE-CIX India Academy. In our last session, we talked about the global IP routing and about unicast, multicast, and anycast. And today I am going to discuss about the DNS, a critical component of the internet. So let's get started. So if you think back some time ago and look at this picture, you remember of your grandma's telephone. It would look something like this. And these telephones even today use telephone numbers. If you want to call someone, you need to know their phone number. If you don't know their number, you have to look it up somewhere. And yes, it there used to be a printed phone book back then. Some of you still might remember them, but today they mostly have fallen out of use. Similarly, what we need is a kind of a phone book for the internet. If you see the internet model, let's talk about the network layer, specifically the IP layer. You may remember from our previous webinar about the IP protocol. Specifically in this scenario also, we take the use of IP addresses specifically. So IPv4 for addresses looks like something like this in the dotted notation 192.0.2.1, and wherein the IPv6 is separated with the colons, and it's a longer to read out. So it's nearly impossible to remember and read out these numbers, right? So what we need is an easier way to use the internet. So as you use your web browser, you don't type in the IP address because it's far too complicated. Okay, so you don't remember the IP address at all for the website. So what we do is we type in the website's name. In this example, we type in www.dkix.net. What we need is a phone book for the internet that translate these names into the IP addresses.
Yeah.
So let's go back and look at some of the history that we have. So imagine a phone book that translates a name to a number. You might think it's quite simple. Just create a text file with two columns in it, write down the names in one column and write down the numbers in the other column. And that's exactly how it started. This file was earlier called as etc host, and it still exists in many of the systems today. If you are using a Mac or a Linux system, you might know that in your file system, there's a directory called as etc host. And in a Windows system also, we have a similar kind of a folder in the system32 drivers folder, wherein you have this particular file. So in that file, you could manually enter those numbers and the domain names into it. However, back in the 1990s, when this file reached the 7,000 entries, like 7,000 systems connected to the internet, it became clear that the simple file was just not enough anymore due to scalability issues and also the performance issues that it would have brought, because it depended upon a single system running the entire database locally on that system. So what do you do if a single text file is not enough for you? So you obviously use a database. So in this case, it's a distributed database, which became to be called as a domain name system. The DNS officially was specified in 1987, making it a cornerstone for the internet for decades to come. The work for the domain name system actually began quite earlier, with the first drafts in the RFC being pictured in the 1983. And the idea was to move away from a single flat table of entries and used a tree-like structure, like you can see in the diagram, what a tree-like structure is, and which is what we use today also. This structure includes a domain names that is in a hierarchical format. The origin top level domains that we had were like arpa.com, .edu, .gov, .mil, .org, and from this you can see who sponsored the development of those domains at that point of time. Like for instance, .mil is also a domain which was representing the military at that time. So country domains are also there, like .de for Germany, then .uk for United Kingdom. Okay, and earlier on, these top level domains were being used and are still being used today. And if you consider, .NET is a quite common domain that is widely used even today, which came back a bit later. And the German top level domain .de was registered in 1986. So you must be thinking, where does DNS actually fits in? Okay, so if we talk about the domain name system, which performs the translation of the names to IP addresses, how does it fit into our protocol stack? Obviously, well, DNS originally uses UDP as the transport protocol. Building on top of UDP, TCP is also possible and was introduced in 1987. But since both UDP and TCPs both work on the transport layer, DNS must be working on the application layer as it is uses the transport layer for its working mechanism. So DNS belongs to the application layer, but many of the applications on the same layers are dependent on DNS. So new standards also followed, like we use HTTP also, the same protocol that we are using to browse the internet as a transport protocol. There is also definitions for those secured connections that we use over HTTP, that is the transport layer security, TLS, but that is also a relatively new development. So now let's focus on the principle of the DNS, how originally it's defined. So the principle of DNS starts with DNS over UDP as it is originally defined. And if you remember, we had the video about UDP, you will remember that UDP includes the port numbers, wherein DNS uses a well-known port number of 53. And initially, the DNS packets were designed to have a maximum size of 512 bytes to avoid fragmentation, because fragmentation occurs when a packet size is too large for a link, requiring it to be split into smaller packets and reassembled towards the destination, which was something we wanted to avoid, as the maximum size was set to 512 bytes. However, today and for quite some time, larger packets are also possible, and they might be fragmented, which can cause problems sometimes, but that is uh, up to the network how it handles it. But DNS was invented to basically translate the names to numbers. But over a time, a lot of additional features were added to DNS. And for this session, we'll only focus how DNS translates the names to the numbers. So let's see how DNS basically works. And the first topic, how it will work, we'll start off with queries. And I'll start explaining how DNS queries for an IP address. So if you can consider a typical home setup, like you can see over here, there's a laptop, there's a Wi-Fi router connected, and in turn, your Wi-Fi router is connected to your ISP. So when you want to visit a website like www.dkix.net website, you type in the name into your browser and your laptop sends a DNS request packet to your local router. Your local routers runs a piece of a software called as a DNS resolver. This is the resolver's job, basically to forward that or resend the DNS query to your ISP, wherein your router connects to the internet and gets the IP address of the DNS resolver from your ISP. Router doesn't manually configure its own DNS. That information is being provided by the default gateway, and that is being sent out via the upstream ISP connected from that local Wi-Fi router. So in this case, your ISP's DNS resolver might know the IP address of DKIX.net, might not know actually. So it breaks down your request to different parts, into different segments. It knows to start from the top level domain, that is the .NET. So the resolver first asks the root name servers. So at the top level of the hierarchy, that where can it find the .NET domain name? So what the root name server responds to the IP address of the top level domain name to the resolver of the ISP. And the next step is that ISP now queries the top level domain name and addresses the DKIX.net to the server .net, wherein the IP address of the name service handles the .net DKIX.net domain. So what the information the resolver's IP got from the root server is being forwarded to the DKIX.net name servers with the DKIX.net zone name. So finally, the resolver at the ISP sends a query to the DKIX.net name servers, which responds back to the DKIX web server, that the answer is then cached to the ISP's resolver. So if another queries for the DKIX.net comes, so it can respond immediately without repeating the entire process. So as you can see, the resolver has cached the entries, and automatically whenever there is another request coming in, so it won't have to repeat this entire process again to query the entire host name for the particular DKIX.net website, and automatically it will deliver it to the laptop. So the resolver handles the answer back to your home router, which also caches it for a certain amount of time, and your router then sends this answer back to your laptop, and now the laptop also knows the IP address of the DECIX.net website and can access the website independently. So this caching mechanism is crucial to the DNS because it means that once answer is known, it can be reused for a certain period of time, and subsequent queries and speeding up the process of the subsequent request. So this is how basically a DNS resolves a name to an IP addresses effectively. Moving on to the next slide. So we can see that there are two modes of operation for the DNS. One is recursive and one is non-recursive. So I'll tell you what is a recursive entry. Recursive entry is used when your computer or your router asks the DNS resolver for an IP address. It expects a complete answer and doesn't want to go through the step-by-step process of finding it. The resolver will ask the name server on your behalf until it gets a definitive answer and finds that it's in your cache, or it will query it for you. And there's a non-recursive query. Non-recursive query typically involves your service provider, wherein it looks for the DNS server in the step-by-step process of querying different name servers until the resolver gets the IP address with the authoritative answer for your query. So your computer typically uses the recursive queries, while the ISP resolver may use non-recursive queries to gather information from multiple DNS servers for your queries. So ISP's DNS resolver must be able to do both of the functionalities, that is the recursive one as well as the non-recursive ones. So in the next part after the queries comes the zones. So what are basically zones, you would ask? So basically, a DNS zone is like a folder of information within the domain name system. Just for example, I'll say that DCIX.net is a zone name. Okay, and it's like having a table list wherein it corresponds all the IP addresses belonging to the DCIX.net domain, and the server managing that zone has all the correct and the official information about it and ensures that there is no confusion about the IP address belonging to that particular zone. So in reality, a zone is nothing but a file or a database that you would say.
So do I need to top up that?
I would request the audience to be on mute so that there is no disturbance. Okay. So unlike your computer's host file that we discussed earlier, this is also a static entries that you could say, wherein the DNS zones are spread across many servers worldwide, and each zone has the main server that oversees it. But these services are managed by multiple zones, especially for like if you consider a big country level domain like .net or .de, so they are having multiple zones deployed, wherein they can have the same information, but it's spread across each and every different geographical regions. So next we could talk about how our zone file exactly looks like. So first we will talk our zone record looks like. To begin with, the zone record starts with the SOI record types. SOI means nothing but the start of authority, and these values numbers are very important actually, if you could see. And the next example in it's nothing but the host name that it's present. For example, the server, these values, that numbers that are very important for the start of authority. So this is unique pertaining to each and every zone. So in this example, I'm taking the example of example.com, wherein you can see that there is a name over here mentioned that is dns.example.com. That is nothing but the name of the primary name server that you can see. And this entry is actually an email address in the next column, wherein the hostmaster.example.com is nothing but hostmaster@example.com. And this email ID is the one which is responsible for this entire zone altogether. Then we have another section in the zone that is called as the serial number section, wherein it helps the name server to keep track of the changes. Of course, you can manipulate that into the text file, but if something is getting changed and it is a resource intensive task, so obviously it has to be a different serial number whenever there is a different change for that particular zone. Otherwise, the name server won't pick up the change. So in this case, if you see the serial number is nothing but a date that is specified 2020, 2021, that 11, then 02, and that's then subsequently the first change, that is 00, that is being put into the serial number for quoting the change number to it. Then the next comes the change refresh column into it. So refresh is often used in the secondary name servers, wherein they will pull the information from the primary name servers for information. And what they do is from time to time they copy the whole zone from the primary and also available to other zone servers for querying about that particular zone. So in this example, the refresh interval is kept to 24 hours. So it will after every 24 hours it will query to the primary name server and take a copy of that particular zone and replace it with its existing one. And it's done automatically. No manual intervention is being referred onto it. And this refresh interval can also be manipulated according. The next value is the retry value, and subsequently we have the retry value. I'll just explain what it is exactly. The retry is nothing but if a secondary same server cannot contact the primary server, it would wait for that particular amount of time so that again it could query for that particular zone to the primary server. In this case, it's 7,200 minutes, precisely 2 hours it is being specified, 7,200 seconds. Okay, so then we have the next column that we have is expire. And expire, this is also pertaining to the secondary name server so that it can, when it could contact the primary name server, the zone gets invalid actually. So the default value is about 2 days, which has been kept here. And the next value that comes with it is the minimum value, and the minimum value is the default value for the entries. Like you can say that it's a time to live value for the entries that is kept in the cache, and usually the value is for 2 days, and it's a quite a big reasonable number actually. And you can lower it according to your convenience if you want. You can lower it to 60 minutes or 1 hour depending upon your preference actually. So the next entry that we have is the NS entries. NS entries are the entries which we already talked about, and we already know that the primary name server for the SOA entry and any zone must at least have 2 name servers. These are also pertaining to the secondary name servers that we are talking to. So in this case, like you can see the top level domains that any zone must have at least. And here you can see that ns.dekix.net and dns-dekix.net are the 2 NS entries for your reference. They must be also listed into the parent zone. In this case, that is a .NET is the primary zone that is already listed. And then finally, we move on to the IP addresses part of the DNS. So wherein you can see the IN here stands for the record here, and A stands for the IP address part, and the 4 times A stands for the IPv6 part of it. And Academy server 1 is just nothing but the host name over here, and how the particular host name is mapped to the particular IP address you can see over here in the A record. And in the IPv6 record, it's a different IP address that is being appended over here. This process is automatically happens. No manual intervention is required to do for this change. So what else do we have? Something called as the MX record. So a mail exchange record is also into the DNS record. So here we have the zone, and on the left hand side you can see the priority of 10 over into this exchange record, and I can give a name of the host which accepts the email, which is given on the right hand side of the email. So next is the CNAME record. There is a possibility to put an alias also to your record, and that's nothing but a CNAME. So in this example, you can see that we have given an alias as a Peter to that particular host name, that is paul.example.com. So now we know that how to translate a name to a number. You just query a resolver and ask for a record or a code 4 times a record if that's an IPv6 record. And this information either works by the resolver having the information already in its cache, or it recursively queries for the answer from different of the name resolvers. But you might ask that what about the other way around? If I want to query an IP address and then a reverse lookup for a host name. So that's when uh, we look for a reverse mapping to the DNS. So in this case, reverse mapping is also there in the DNS, and special top level domains are defined for that. And in this case, in-addr.arpa for IPv4 and for IPv6, IP6.arpa is being used, and a special record type is used for this entry that is called as a PTR entry. So how does this reverse query actually works? So from a user standpoint, if you have done any lookup query for Linux, if you can see dig-x with the IP address, you could get a reverse query for a particular host name. In Windows, you generally use an ns lookup command to query this particular lookup. How exactly does this function? We'll have a look into it. So when you query for an IP address, it's actually the most important part is on the left-hand side of the IP address, and it's hierarchical. But when you consider a domain name, the most important part is on the right-hand side. Okay. So in this case, nothing happens, but we swap the entire label onto the opposite side, wherein when you query for 136.121.31.46, it automatically return backs the answer to myserver.example.com. It's that simple. So this is the hierarchy that I specified almost earlier also, that the most significant part is on the left hand side, and in the domain name it's on the right hand side. And for the IPv6 also it's the same thing only. So whenever you have a DNS entry for an IP address, you better think of automating it or match the forward entry with your reverse entry. But that's a tedious job. But at least make sure that you have the reverse entries to the specified IPs that you wish to have a reverse lookup query with. So next up, let's talk about the DNS today, and how was we talked about the history of the DNS, but let's see how DNS has gone through recent times. So as we have seen that the technical aspects also for the DNS, that your DNS resolvers are working for the customers, and a router automatically picks them up. You don't have to worry about anything, and you just connect your laptop to your router and everything works automatically. But for instance, if you are unhappy with the DNS that your ISP is being provided, so there are many of the public resolvers that are available. Like for example, customer might be knowing that we have a Google Open DNS, we have Cloudflare's Open DNS, and a Quad9's also Open DNS. And you could Wikipedia this also for many of other of the public Open DNS. So this DNS offers some additional functionalities which they claim, like for instance, they can protect you from malware, or Google in this case, when they give you a public resolver, of course, they are not uh, only giving you this resolver help, not only to resolve the host names to the IP address, but they also use it for their own statistics. And the statistics can also be monitored by your ISP. Clearly, they are not spying onto your any data, but clearly those lookups are valuable to them, whether what of the data is being users are frequently watching to. So recently, DNS over HTTPS S is also defined, and yes, the HTTPS is the same protocol that you use for browsing the internet. And the idea behind it is not a better user experience, basically, but moreover, a control for the people who is supplying the DNS to you. So another technical aspect to the DNS is the DNS-SEC feature. The DNS-SEC is a recent extension to make the DNS more secure. DNS-SEC is a way that you sign the DNS zones cryptographically and authenticate it with a public key, and the resolver receiving an entry can really verify that the information is coming from a correct source. And keep in mind that a lot of things are cached, and lot of things are cached. And how does the end user or the computer of the end user know that the answer it is being cached is from the actual primary web server? So this DNSSEC actually comes really into picture at that point of time. Otherwise, you can see in this diagram also, if there is a cache poisoning and attackers tries to inject wrong entries into a resolver by sending some false replies to an IP address. Uh, so that would be a very disastrous in that case, and customers would be redirected to some other page rather than intending it to some actual page towards the destination. So when you consider on a non-technical standpoint over the DNS, so DNS acts as a central function to the internet, and it's often used as an instrument of censorship to avoid and to suppress some unwanted content. Like for instance, you can tell the ISPs to suppress some unwanted content so that they could generally what they do is just suppress those websites to resolve those host names, and obviously customers and users won't be able to access those particular websites. And remember that DNS only translates domain names to IP addresses. And you can also do the translation yourself locally with the etc file that you have locally on your system if you would, if you want to. So coming up to our conclusion, let's sum up the things that we have covered. That DNS maps the names to the numbers, and here for the example, www.dkix.net translates to some IPv6 IP address when you look up via DNS queries. Then the domain names are hierarchical like a tree-like structure, wherein the top level domain root domains are the .net, .com, ARPA, edu, and all of them. Then the second level domain are the dkix.net and the other .net domains. And the third level hierarchical structures are the websites and the host names that belongs to your domains. And also DNS gives you the functionality to reverse map the IP addresses back to the host names, like mapping this particular IP address to this in the example that I've shown in the slide. So DNS is a complex system and was extended a lot over the time, but DNS itself is a big topic that won't be able to cover even in a week's time, I believe. So this was just an overview to give to our customers that how DNS basically functions and how internet, how DNS plays a crucial part for browsing the web. Thank you, everyone. I hope this session was informative to you. Um, any questions, if anybody is having, we are ready to answer them. Yeah, over to you, Rishabh.
Suraj, I think Avesh wants to ask some question. He's raising his hands. Avesh?
Yes, Apu. So, Apu, I just want to know, how does the root server, like, as you have explained the DNS concept, so how does the root server knows where is the IP and where is the domain pointing and where it is exactly located?
So the root servers are basically those servers are all hosted on the internet only. So those they have the information about the top level domains that actually are there. So for instance, when you queried for a .NET website, so the root name server gave you an information that .NET belongs to that particular zone wherein this DNS resolver has that information. And when the .NET resolver had that information, it queried pointing towards the DE-CIX resolver hosted on the local premise. So these generally are not based out of any local repository or any local servers in the DE-CIX domain, but on the internet they are hosted.
So, who feed this data to the root server?
What?
So basically, all the information is available in the root server, right? So, like, is
Yeah.
there any manual configuration done on the root server, or it is generated automatically?
No, it's automatically. The root level domains are already being informed, and they have n number of clusters among them, wherein the root level domains communicate with each other to specify and redirect your query to the specified local. a cluster of the .NET domain that you are about to query on the second phase. No manual intervention basically is required in this case.
Okay, thanks, Apu.
Yeah, thank you, Anvesh.
Apu, there's a question in the chat box. Can you please resolve that query?
1 second, I'll just check.
It's TSPL. He's asking for the advantage use of ISP DNS server.
Advantage use of ISP's DNS server. Okay, so the basic advantage of your ISP's DNS server is, first thing, the things that are localized to the ISPs are being served to you first. For instance, if you are using a non-ISP DNS, like for instance, you are using a open DNS, that is a Google DNS. So there are some services which are localized to the ISPs, like there is Akamai caching, there's Google caching, and there's n number of caching that are deployed on the ISP's network. So those IP addresses are being preferred via the local DNS first for the queries, and then the Google domain, the open DNS. And for instance, sometimes the open DNS doesn't even query those caching servers IP to you, and your traffic may be redirected toward the internet rather than taking the local part towards the caching or towards the peering. So that advantage we have if we are using a local ISP DNS server. First thing. Secondly, a second advantage also you could consider for ISPs DNS server is that they have their own speed test servers also, or some local deployments also, wherein they redirect those IPs so that you could have a better user experience when accessing those services. Okay, so preferably a local DNS of your IP address of your local ISP is being preferred. That's what general use case scenario is. Any more questions anyone is having? The next topic that we have for our upcoming webinar on the 25th is on HTTP, and that would be our last topic on the networking basic series. And then we would be moving on to some advanced level topics that we will update you about the same over our DE-CIX India website as well.
Thank you for watching.